Thank you for watching Knowledge Academy. Today we are here and we're going to be starting a new topic which is called tangent planes and normal lines. And what exactly this topic is a simple topic, but it has a detailed concept. What this exactly topic means. You taking a shape, any shape, like you have a potato shape, and what you're doing, you're taking a plane, right? You're taking a little patch and what you're doing, you're taking this patch maybe and then it's stuck and then try to touch with this surface. So it's going to be look like here, it's going to be look like here, it's going to be look like here. You're taking this patch, which is, if you see from the side, it's going to be look like a line, but actually this is a 3D patch. I'm going to call 3D surface. And if I say 3D surface, this is also 3D surface. I'm going to distinguish between the two. I'm going to say this is not a surface. I'm going to make a little small flat plane. So I'm going to call that plane rather than surface. If you remember, we talk about that plane versus surface. Surface doesn't have flatness necessary, but plane have a flatness. It should be flat. Plane cannot be curved like this. That cannot be. This is not a plane. So I have a plane, little plane, and I'm just passing this plane into different point. And what I'm doing, I'm trying to actually draw this potato shape by using this plane tracing. So I'm tracing. I'm tracing. Like what I mean by tracing is every time when the plane touches this potato, I'm taking these points. So if I'm taking all these points, and after that I'm going to be connecting these points. I'm going to be saying, you know what? Look like this is something, look like this shape. I really don't care if it's a potato or some other shape. I just want a parametric form, like numerical model of the surface, right? It's just like some blind person. Some blind person want to see how a car look like. What is gonna do? A blind person want to know how a car look like. What he's gonna do? He's just gonna go and start touching the car all over, and he passing his hand or she passing his hand, and that the whole car is basically being traced by their hand. Yeah, maybe they don't have a clear picture of how this thing look like, but computer is very smart. Computer is very smart. So if you have a scanner, if you have any scanner, you can pass this thing on the surface. The computer actually draw a 3D, it actually draw a 3D model for that particular car. Now, since we are talking about in 3D, I'm going to be making a shape like I'm showing here. I'm taking like a surface, like the blue one. It's very hard to show the 3D, that's why I use this image. But in this image, you can see this little patch, the orange patch. This is my plane. Now this plane have an equation. This plane also have an equation. So what I'm going to be doing, I'm not going to be taking the whole plane. I'm going to be taking a line on the plane. Maybe this line, right? Maybe other line, right? Any line I take it, and there is a line, and I'm going to take a little patch, and then I'm going to stick here on the patch and then pass. So what's happened? When I make this line, which is this one, this line, there is a tangent on this line. Tangent means when I take the partial derivative, or I can say gradient, right? This gradient actually producing a tangent. Gradient always producing tangent. So if I do dy over dx here, is going to produce a tangent. Maybe it's going to produce a tangent. It's going to produce a tangent. But since I have a surface in 3D, and I do this, I take the derivative in 3 different directions. So really, if I call it to, taking the gradient, this gradient is not going to be tangent on x and y and z. It's going to be tangent in all 3. So really, it's going to be sticking out. This gradient is going to be sticking out. That's an important point. This gradient is going to be sticking out. So if I make a tangent on the surface along the line, just remember there is a curve here. So there is a curve here. So I'm going to take the point P and take the gradient on that point P. So it's going to be tangent to that point, which is this one. Now I'm going to be taking a tangent or position vector on this particular point along the curve, not along the surface, along the curve. It's going to be making like this. And you can see these two are 90 degree apart, 90 degree apart. So if I'm writing like this, right, if I'm going to be writing like this, dot this vector, the dot product must be equal to, must be 0. Right? Dot product must be 0, and that is our, we create the equation. So I'm writing the theorem. Okay, I'm going to writing a theorem of same thing. And let's see how this theorem is going to be look like for this particular topic. I just want to keep this thing here so we can see this image while we're writing the tangent plane and normal plane theorem. I'm going to be writing here theorem, or basically it's equation of tangent plane. Okay, equation of tangent plane. If f is differentiable, the function if f is differentiable, the function is differentiable at some point, which is p here, and I'm going to say is x naught, y naught, z naught, then the equation to the surface given by z naught is this. Remember, this is just a dot product. So take this equation, and then I'm going to ask where this equation came from. We're going to go and revisit the thing we just talked about on the top, the dot product. So really I'm taking a dot product plus fy of the function x naught, y naught, z naught, and y minus y naught plus z x naught, y naught, z naught, z minus z naught, and the most important thing, they should be both equal to 0. So really what we did here, if I go back here, this is my gradient, this is my gradient, right? So this is my gradient, this is my gradient, this is my gradient component. These are the three components, x, y, z, right? This is my partial derivative of function with respect to x. This is my partial derivative with respect to y. This is my partial derivative with respect to z. And the other part, this one, this one, this one. Actually, this is a position vector. And if you remember, the equation of the position vector is x equals to x naught plus at, right? Y equals to y naught plus bt, and z equals to z naught plus ct. Those equations. So the part came from that equation is my position vector. Or really I can say these are the two coordinates, I just take the minus. Remember, I use this vector as a unit vector. So it means A, B, C all are equals to 1, 1, 1. So that's the equation they came out. All we did just taking the dot product between the two and multiply them. Make sure the key here, you should writing this in your answer. Every time you solve your answer is going to be look like this. Maybe plus 3 is not enough. You have to write this. It's going to tell me this is equation. This is a critical part. Usually students forgot that part. But let's do some problem so we can understand this topic a little bit better. Find equations for the tangent plane and normal line. Two particular function is given: a x squared plus 4y squared plus z squared equal to 12 at some point right. One thing we already know by looking the equation, this is a plane. This is a plane. X squared plus 4y squared plus z squared is a surface, and it's a 3D surface. We can tell by looking it's a 3D surface. I really doesn't want to draw how does it look like, but whatever the shape is going to be look like, I want to make this plane at this particular point. So what should I do? I'm going to be taking I'm going to say my function is this, and I'm going to be rearranging them a little bit. So maybe I can take the 12 on the other side. And then I'm going to be taking the gradient. And can I take the gradient directly? Right? You can do this way. If I want to do in the vector form, I can do it differently. You can do this way, or I can do directly in a vector form. That's what I'm going to be doing here. I can make this and I can make the vector. Parentheses, then I'm going to take the first, right? I'm going to take 3 derivative with respect to x, y, and z. So the first one, if I take with respect to x, this one is just 2x. And everything else will become 0, because when I take the partial derivative with respect to x, y and z considered as a constant, and the derivative of a constant is 0. When I take the y, the x is considered as a 0, the z is considered as 0. Only the center term will be used as a variable. So I'm going to be taking 8y. The third one will be 2z. That's about it. Now, since I need the vector in a particular point, that's why I wrote x naught, y naught, z naught in a definition. If you see here, I wrote here these points, and these are the points for this coordinate of this P point. So what I'm going to do, I'm going to go and then substitute the value for these 3. So I'm going to write like this, and writing 1, 2, minus 2, 1, minus 2. And if I substitute here, it's going to be look like 2, 2, 8, 1, and then 2 minus 2. And if I further simplify it, it's going to be 8, 8, and 4, 8 minus 4. 4, 8 minus 4. Okay. That is my pretty much half of the calculation is done. Now I want, this is my gradient, right? Gradient of f. Now I want the plane equation. The equation of plane we already know. We're going to be writing like this. It must be equal to 0. In this thing, I think I have everything is given. So I'm going to substitute the value. Maybe I can go here and substitute the value. So it's going to be 4 x minus x naught. So x naught will be 2. Just I'm going to write here. This is my x naught, y naught, x naught. And here is 4 and then 8 plus 8. Then y minus 1. Then minus 4. Z plus 2. And don't forget this guy. Right? That's pretty much what I got. For my plane equation, that's my plane. I'm going to go to the second part of this problem, which is fairly quick. We already knew that. We learned that long time ago. We just need to reuse that strategy. And that is my line. Which line? Parametric line. Or I would say that parametric equation. We're going to be using here parametric equation. And this equation is equals to x plus at, y equals to y naught plus bt, and z equals to z naught plus ct. Okay. Now a, b, c we already being determined, right? It's given in the problem. In this particular case, we're going to be use this one, a, b, c. So I'm going to be writing this equation like this. X equal to x naught plus at, so x naught will be 2 plus at, which is my a is my 4t, which is right here. This is my a. I'm right here maybe a little bit different color. So this one is my a. This is my b, and this is c. Yeah. So I'm going to be writing here y equals to y naught, which is plus 8t. 8 is my b, and z equals to z naught. So z naught will be minus 2 minus 4t. And these are my equations of lines. Okay. Let's take a look and another problem. So your tangent line, tangent plane and normal line. Okay. Now, one question before we moving forward with this problem. Sometimes students asking if the problem is only asking about normal lines equation, right? Normal lines equation. So technically speaking, you must need a normal plane equation, or at least you need to do the gradient because you need A, B, C. This A, B, C is not given unless and until you find the plane equation, right? So if it's not given, then you have to find the derivative or partial derivative or the gradient to finding ABC, just like we found here. This ABC is not visible until you solve this gradient in that particular given point. So if somebody asking you in the question just a plain equation, you can do it. If they're asking about just a normal equation, normal line equation, you have to do a little bit work before you get there, right? Or if the question give you ABC, that will be fantastic. So let me just do this and go here, solve this one. I want to be doing my function. So my function is, I need to rearrange the equation. It's going to be look like x squared plus y squared minus z and minus 12 equal to 0. That is my equation of my surface, right? I'm not calling it plane, I'm calling it surface because it's a 3D shape. Then I'm going to be taking partial derivative or gradient. It's going to be 2x, 2y, and minus 1. Then I'm going to be taking the gradient and substitute the point. It's going to be 6, 4, minus 1. Now I'm going to be writing the plane equation. I'm going to say normal plane. And it's going to be, I'm going to write the equation one more time so we remember. And this one is x, y, one is z. Oops, z minus c must be equal to 0. Let's substitute everything here. So I'm going to substitute this one is 6, x minus x naught. So x is x minus x naught. X naught is 3. Let me just substitute here again one more time. A, B, C is going to be used this one. And you can also call this one is my fx, fy, fz, right? This is what we are using here. And this is my x naught, y naught, z naught plus 4 y, sorry, wait, a bit off. Let me just, it's going to be 4 y minus 2 plus 1, right? And it's going to be minus 1 here, and z minus z naught, so z minus 1. If I solve this one, it's going to be look like 6x. You can solve this, so it's going to be 6x minus 18 minus plus 4y minus 8 minus z plus 1 equal to 0. So I'm going to be simplified further because I can and here is 18, and minus 8 will be minus 26, and minus 26 plus 1 will be minus 25 equal to 0. And that is my plane equation. Let's move on to do my normal. X equals to x naught plus et, y equals to y naught plus bt, z equals to c naught plus ct. And is going to be x equal to x naught, which is 3, plus at, so 60, y equals to 2 plus bt, which is 40, and z equals to z naught, which is 1 minus ct, and c is minus 1, so it's going to be minus 1 and then just a t. And that is my equation. So in our previous class, we were talking about equation of tangent plane and normal lines, and equation of tangent planes. Is it in something look like this? You're writing fx, x naught, y naught, z naught. I just want to add one more thing. In these equations, you should not be substituting these values. Let me just finish writing this. And y minus y naught plus fz, x naught, y naught, z naught. And this one is z minus z naught equal to 0. Now, one thing I'm going to be adding here is you do not include these partial derivative without substituting the value. So let's suppose if somebody could give you the point in the question, if the point is given, you should be solving these partial derivative and finding a digit, let's suppose 14 or 13, whatever. Then you're going to be substituting here. So really, if you notice one thing, same point goes here, and then all three coordinates go here. Then same points go here, then all three. So really these two things are common. And then rest of the two coordinates is coming from the question. Because if you're not substituting the value, you have a variable here, maybe like 4x squared y. There's a variable here. And and then when you're just trying to do maybe adding 2 here and you try to solve this, it's not going to be a true equation because you already given the x naught value in the question. Okay, so make sure you solve these equations before you substitute in the values. And the other equation we talk about normal lines. And what is a normal line equation? Normal line equation is nothing but, let's suppose I have a crazy kind of shape. And I'm asking you, can you give me the tangent plane on this particular point? All you have to just go here and make a little patch. Right? This little patch is going to touch on certain point, and then this point you're going to give me the equation, and the plane of this yellow equation, that is a yellow equation, right? And after this, give me the yellow equation, you're going to give me the equation of a tangent plane. Normal line. So normal line equation is going to be some line to this plane, maybe this point. And this is basically is nothing but is just a parametric line. And you're going to be using this equation, x equals to x naught, x plus naught plus at. Let me see here. Using three equation, x equals to x naught plus at, y equals to y naught plus bt, and z equals to z naught plus ct. Again, these 3 points are the point for this coordinate. A, B, C are the vector. You want to be taking the vector. So this white color vector, maybe it's like looks like it's straight, but if your plane is look like this, let's suppose you want to make another plane here. No. And this in this case, this normal vector to the plane, it has 3 components. If I'm going to draw here, no, it has 3 components. You can draw here just like that. So that is your A, sorry, that is your Y. So that is your B. If you come here, that is your A. If you go here, that is your C. Okay, so these are the 3 coordinates of this vector. Let's take a look at another problem. Find the equation of the tangent plane to the hyperboloid. The hyperboloid is given like this, right? At a point and this is a point. Okay. So first thing first, I need to find out my equation is given. It's written like this. We can also call this is a function for x, y, z. And if there is a constant somewhere here, you have to move on the other side to make it like an equation form. So we have what we have. We have this fx. If I take the derivative with respect to x for this equation, the answer would be 4z with minus sign. 4x with minus sign. And if I take the derivative with respect to y, the answer would be minus 4y. Same thing if I take the derivative with respect to z, the answer would be 2z. Okay. Before you substituting this value, I must have to solve them, and I'm going to add in the point, which is this point. And this is my x naught, y naught, z naught. Okay. So I'm going to substitute the value fx 1 minus 1, 4 equals to minus 4 and 1. So we're going to be just writing minus 4. Same thing fy, I'm going to be adding 1 minus 1, 4. It's going to be minus 4 times minus 1 is going to be 4. In a similar way, we're going to do the fc, which is 1 minus 1, 4. And if I substitute z value of 4, 4 times 2 will be 8. Okay. I'm going to write here This is the standard equation of tangent plane. I'm going to be just substituting the value. So this is a partial derivative of this, right? This guy is this. Then this is fy and this is fz, and x minus x naught. So x naught is this. Phi minus y naught is this. Z minus z naught is this. So let's substitute these values here. So partial derivative of function with respect to x, the answer was -4, and then x minus x naught, and x naught here is 1, then plus partial derivative of the function with respect to y, which we solve with 4. I'm going to write here 4, and then y minus y naught, but here y naught is -1, so it's going to be 1 with plus sign. Minus minus is plus. Then plus partial derivative of the function with respect to z, which we calculated 8, and then z minus z naught, and z naught here is 4, and everything must be equal to 0. My function my equations look like can be simplified further, so I'm going to just keep moving forward and see if I can further simplify, and it's going to be 8 z minus 32 equals to 0. So I'm going to be just writing all these variables first. (32) with minus sign, and then 4, and 4 is plus 8, minus 32 will be minus 24. I can further simplify it by taking divided by 4 maybe. So if I divide by 4, the answer would be, or maybe -4. The answer would be x minus y minus 2z and plus 6 equal to 0. And that is my equation of the tangent plane. All right. Now in this problem, we're going to be finding the normal plane and normal line and the tangent plane both together. So find the equation of a tangent plane. This is A part. Find the equation of the tangent plane to the surface at a given point. Okay. And B, find the set of symmetric equation for the normal line. Okay, at a given point. And the data given to us is this linear surface. The point is given is this. Here what we're going to do, first we're going to write the function. So my function is x squared plus 2y squared plus z squared minus 7. Yeah, so it's going to be 7. And everything is equal to 0. Now I'm going to be taking fx, fy, fz. So fx at x, y, z, and fy, x, y, z, and then fc at x, y, z. Let's do all three simultaneously. The first one will be 2x. The other one with respect to y will be plus 4y. And the last one will be just 2z. If I substitute the values for fx, fy, fz, is going to be fx at 1 minus 1, 2. And the answer will be 2. The fy at the same point, the answer will be 2 again. It's going to be minus 4. So minus 1 times 4 will be minus 4. And fz with 1 minus 1, 2, the answer would be 4. 2 times 2 is 4. Okay. So what you're going to do, we're just going to substitute the value into the equation. So in A, we says partial derivative of this so 2 x minus x naught. So my x minus x naught is 1 and minus 4 y minus y naught. The y naught is minus 1, so it's going to be plus 1. And then z will be 4 z minus z naught. The z naught will be here is 2 into 0. We can further simplify 2x maybe minus 4y plus 4z. I did one drag step. I just multiply all the variable first. Then I say the second one, which is 2 minus 1, sorry, minus 4 and minus 8 go to 0. We can further simplify this equation, and equation probably looks like 2x plus minus 4y for z minus 6 and then 14. We can further, can we do that further divided by 2? So it's going to be x minus 2y plus 2z minus 7 equal to 0. And that's pretty much what we got. Now second part, they're asking about symmetric equation, not parametric equation, symmetric equation. Okay, the part B, they're asking about symmetric equation. And symmetric equation is look like this: x minus x naught over a equals to y minus y naught over b equal to z minus z naught over c. Something look like this. So I want my equation to be in this form. So what I'm going to do, this actually another form for this one. It's just a review of an old concept. And from here, you just remove the t. If you remove the t here, t equals to x minus x naught over a. T from here is y minus y naught over b. And t here is z minus z naught over c. And if you make these all t's equal to each other, you probably ended up for this equation, right? So what I'm going to do, I'm going to be just finding the symmetric equation, parametric equation, and then drive the symmetric equation from them. Okay, here I have x equals to x naught plus a t. Now, we do not have a particular, we can use this point if you want to take this point and maybe make other point like 0, 0, 0 for that particular normal vector, right? And same thing, we're going to be just finding y equals to y naught plus bt, z equals to z naught plus ct. Here a, b, c you can find, you can substitute the value from this, or you can consider a vector, maybe you can taking a point 0, 0, 0, and then minus them, and you can find out this one and substitute the value so you can find the equation. There is another concept we're going to be talk about, which is a little bit difficult for this normal plane, but it's the same application. I'm going to be jumping into that. Another use of the gradient So really, if you think we are talking about right now the application of the gradient is to determine the angle of inclination of the tangent plane to the surface of the tangent plane okay. And what does that mean? It means if I draw here, this is my x, this is my y, this is my z, and let's suppose I want to make a normal plane, right? So I'm going to be making like a sphere, like a ball. A sphere, it's a 3D sphere, okay? And I'm going to take 2 points. Number one, I'm going to be taking a little patch, and I'm going to ask them, can you touch this patch over here? You touch here. And I'm going to ask, can you move this patch over here? Can you touch here at this point? You're going to be touching maybe somewhere here. Right. So you can see they change the direction, or I'm going to say a word called orientation. Orientation. Really, this whole concept, the one we are going to talk about, the inclination or angle of inclination for the tangent plane to the normal. What we're trying to do, we just find out how much this plane is changing with y-axis. So this is my z-axis, and I'm gonna consider it as z or y. In 2D is y, 3D is z, and I'm gonna ask myself how much the normal. So every plane have a normal vector. So I'm gonna make normal vector this white color vector. There is another vector called white color vector. Maybe I can put the plane here too. And this white color vector is going to come out like this. And this white color vector basically is normal to the plane. Normal to the plane. Which plane? This yellow color small yellow color patch plane. Really what this concept is, they want to asking you how much you rotate your plane. This is the whole concept is all about how much you're rotating this plane. So if I'm going to take this example, maybe just make another way, like this way, make like this. There's a little patch. And right now, patch is basically on the floor. Right, this patch is on the floor. I put it on the floor. I start asking you to rotate this patch a little bit, and it's going to be look like pretty much this. So you rotate this patch. So you rotate how much? Theta. And if you want to do another way, you can see from this side. If you want to see from this side, it's going to be look like this. Let's suppose this is a edge called A, B, and this is called, this point is A, again is called C. So it's going to be look like this. Right? So this is A, B, and this side is C, AC. But if you want to, more elaborating this one, so there is a normal of this point is going to be look like straight up, right? It's going up. And if you want to make this another point, you're going to make it here. Maybe I can change the color to the red color one, like this. After rotating, you want to make a vector like this. So the red color vector is this, and the white color vector is this. Really, this whole concept is this angle equal to this angle. And this theta is called angle of inclination. Angle of inclination. We call this vector, and the white color vector always straight. We keep all this white color vector, we keep always straight, and this white color vector is along z-axis. White color vector is along straight, like vertical, and is along always with z. So this z vector, we should call it k, because k is a unit vector for z. And this vector is always normal to the plane, so I call them n. Right? It's called n. So really, I want the angle. I'm going to say theta. I can write another way. I can write theta. Angle between normal vector and k. Theta is the angle between normal vector and k. So really what I'm going to do, I'm going to say by using dot product, I'm going to use the dot product strategy, and I'm going to write here n dot k, because both are vector. I'm going to take the derivative, the dot product applying, and dot product equals to n magnitude times k magnitude cos theta. And this theta is my angle of inclination. Okay. And how can I calculate? I say cos theta equals to n dot k magnitude divided by n magnitude and k magnitude. Since k magnitude is 1, I can also write this. K is a unit vector, so really this is my formula. In this example, find the angle of inclination of the tangent plane to the ellipsoid. An ellipsoid is giving something look like this. At a point 2, 2, 1. Okay. Here I'm going to be writing my function one more time. And it's going to be x squared over 12 plus y squared over 12 plus z squared over 3 minus 1 equal to 0. I'm going to do a draft step, right? Then the gradient of f at a given point. The given point is 2, 2, 1. So if I take the partial derivative with respect to x, is going to be 2x divided by 12, so it's going to be x over 6, right? And I plus y over 6, this is my partial derivative with respect to y, is going to be 2y over 12, so 2 and 12 cancelling out, the denominator only 6 left, and plus 2z over 3, okay, there is a j. So I wrote my vector in the form of the vector in the unit vector form, and I'm going to substitute the values here, which is 2, 2, 1. These are the given point, and it's going to be 1 over 3 plus 1 over 3 plus 2 over 3. Okay. Now that is my vector. Right here. And right here. Because delta f, which is at 2, 2, 1, is normal to the tangent plane. So let's suppose this is a plane, some whatever plane is. This vector, this delta f will basically look like this. That is my delta f gradient. This is the direction of this vector. And the other vector we want, which is normal to z-axis. Remember, I always told you it's always going to stay z-axis. If plane look like this white color line is going to stay there. If plane look like look like this, again this white color vector, the normal, which is k, is always stay there. This is my k, and I want this angle, and I want this angle. Right. Normal plane, and the k is normal to xy plane. Right. This is another way I say xy plane means floor. Like this is x, this is y, this is x. So I'm talking about this floor. So this k vector is normal to that floor. Okay. It follow the angle of inclination. So the angle of inclination cos theta, and two vectors dot product divided by the vectors dot product, because k vector magnitude is 0, sorry 1. So I'm going to be writing here two vectors here. Which two vectors? One should be k divided by, k is also come in the denominator, but this k is becomes 1. So I'm going to leave it for now. But let's talk about what vector is going to come here. Which vector? This vector. Right. Now I'm going to be writing this vector, and I'm going to be writing 1 over 3 I plus 1 over 3 j plus 2 over 3 k. I wrote it for a minute just for think about it. If you take the dot product of these two vectors, what is going to happen? When you multiply I times k, the because I and k, the angle between the two is 90 degree, and cos 90 is 0. So this term becomes 0. For this one and that one, k times k terms, that's the only thing left over. The rest of them is 0. So the rest of them is disappearing because the unit vector I times j, I times k, and j times k, everything becomes 0 except the similar one, like k times k will be left over. So what I'm going to do for easiness, I simply can just write the k term, right? And that is my n vector, normal vector. So I'm going to be writing here is 2 over 3 k really, which is the last term right here. And in the denominator, I need the whole vector, right? In the denominator, I need the whole vector. So I'm going to write like this. Maybe I can just write like this. I need the whole vector. So if I simplify it a little bit further, cos theta equals 2. It's going to be 2 over 3 because k times k becomes 1. So 2 over 3 left. And 2 over 3 magnitude is 2 over 3, right? This cannot be, it's because after the removing the mod, it's going to be still positive. In the denominator, this guy becomes 1. So I'm going to write here 1. But here I'm going to be writing this whole vector magnitude. And the reason I just explain it in a little bit detail, because students usually make a mistake. They're writing here 2 over 3. They also writing 2 over 3 in the denominator. You know, you need the full vector. Okay, you need the full vector in the denominator. Let's solve it. Since this is a normal vector, my answer should be 1. If you solve it, it's going to be, everything becomes 1, right? 1 plus 2 plus 2. It's going to be 3, 9, and 1 plus 1, 2, 2 plus 4, 6, 6 over. So it's going to be, if you solve it, it's going to be like this. 1 plus 1 plus 4 over 9, right? And if I solve this, it's going to be 2 over 3, and it's going to be 6 over 9, right? You can take in the numerator and then solve it and simplify it. Since I have a limited space, you can simplify it. It's going to be taking the roots on both sides. Now multiply by this. Multiply by this. Oops. I have a and divide it by the same thing. So if you simplify it, that is going to become out this. And here is a cos theta. 2/3. This, I want the theta only, not cos. So I'm going to say is cos inverse 2/3 v square. Okay. If you take this one, it's going to give you the value for 35.3 degrees. And the answer should be in degrees because this is our standard unit. And how it's going to be look like if you want to make a draw. We all know how the ellipsoid look like. So ellipsoid is supposed to be look like this way, right? And if I make this by this point look like 2, 2, 1, so it's somewhere here in the positive range, maybe here, right, like this one. And if you want to be drawing the normal, I'm going to change the color. It's going to be look like, maybe make a little bit bigger. So this red color plane is touching to the white, the yellow colored ellipsoid on this particular point. So I'm going to take a normal into this. So really, this angle, this angle between the two is this angle. Which angle? I'll change the color. Is white color angle. This is what we calculated. Let's take a quick example one more time, the different one. Find the angle of inclination. Given surface at a given point. At a given point. Okay. The surface here is given is my surface is given here is so both things are given. The surface is given, the point is given. Let's jump into that and start. First thing first, I just want to get the direct steps. So I'm going to get the gradient of x, y, z. Okay, this one is equal to 6x I plus 4y j minus k. I'm going to substitute the value of the point, which is 2, 2, 5, and it's going to be 12i plus 4, sorry, 8j. Minus k. Okay. Now I'm going to substitute in the formula is this cos theta equals to the function of the gradient times k. So I'm going to be writing k here, and I should be writing only one. No, and I should be just making one bar because this is the product. And in the denominator, I have the whole vector, the whole gradient vector at 2, 2, 5 times the k vector, which is a unit vector. So this guy is supposed to be 1. That's why usually we don't write it. And inside the other side is going to be writing this one. If you solve this one, we know that everything will be gone. Like this term will be gone, this term will be gone. Only minus k is the one who multiply the k. The minus k times k dot product will be answer will be -1. But there is a mod, right? There is a mod, so I can simplify this one. And if I take the value of this one is going to be 12 squared plus 8 squared plus -1 squared, right? We're going to solve this one. So the numerator is going to only one left with the positive sign. In the denominator, if you solve it, it's going to be 209. I'm going to divide them later, but I'm going to say this cos theta equals to 1 over 209. And if you find theta here is cos inverse 1 over 209. If you solve it, the answer would be 86.03 degrees. Thank you for watching Knowledge Academy. Please subscribe my channel.